Hey everybody, let's talk about radiation. So, some nuclei, which is the plural of nucleus, they are unstable. And not unstable like your Uncle Gary, but they are on the verge of falling apart. And what that means is that they will shoot out different little particles there. So, why does this happen? Well, there's a couple of reasons. One of the main reasons that it happens is that if the nucleus is too big, once the nucleus gets too big, it just gets too hard for all those protons and neutrons to hold themselves together. And the protons pushing on each other becomes too much, and the atom will undergo radiation. There's another reason. You don't have to be a really big atom. All big nuclei undergo radiation, but sometimes small atoms can undergo radiation if there's not the right balance of protons and neutrons. So even a smaller guy like carbon, let's say, can be subject to radiation. So anyway, they're falling apart here. So these particles that when we shoot them out, we call those particles themselves nuclear radiation. And so they get spit out. Radiate from the Latin literally means to come out from the center there. And so that's what we call nuclear radiation. And any atom or element that tends to be shooting out nuclear radiation, we say that these atoms are radioactive. And here you might be familiar with the symbol for radioactive there. So this means when you see this, it's a warning. It's meant for all people across the world to know that this thing is radioactive and it is dangerous because it's spitting out these particles here. Okay, so let's clear these off the board here. Let me just pick the whole thing up and dump it over here. All right. So now, when they first started studying this, they wanted to know all sorts of things about these particles. So one thing you do is you study to see if there's a charge. So they had this lead box here with something radioactive in it, and boom, it was spitting things out, and they were going to study this phenomenon. So the first thing that they noticed was one type of particle that was spitting out was getting bent towards this negative plate. So they had a negative plate down here and a positive plate down there. Well, opposites attract and likes repel. So the fact that it was bent towards the negative plate let them know that this radiation that they were finding was positively charged. Since it was the first type that they found, they named it alpha, after the first letter of the Greek alphabet. So that's a lowercase alpha there. Not too long after that, they discovered a second type of radiation. That type of radiation was bent in the opposite direction. So it was bent up towards the positive plate. Remember, opposites attract. So this second type of radiation must have been negative because it was attracted to the positive plate. They called this second type here beta after the second letter of the Greek alphabet. So there's beta. It looks a lot like RB. That's a lowercase beta there. Then they discovered a third type, and the third type shot straight on through there. So the third type went straight through. They named this third type after the third letter of the Greek alphabet, gamma, and so which looks basically like a Y there with a big loop on the bottom. So alpha particles, positive charge because they're bent towards the negative plate. Beta particles, negative charge because they're bent towards the positive plate. Gamma particles or gamma radiation, no charge because it wasn't bent at all. And one more thing to point out here, the beta particles were bent a lot more than the alpha particles. And so that told them that the beta particles must be much smaller in mass because they were easier to move, just like a pebble would be easier to move than a bowling ball there. So now let's clear these guys back off here and go into a little bit more detail on those three types. So the first type again was called alpha, like that. That is the Greek letter alpha. By the way, you spell it like this. And then what it turns out, we later figured out it was 2 protons and 2 neutrons. And that's why it was positive. 2 positive things, 2 neutral things. And so it had a positive charge there. And an alpha particle, that's basically 2 protons is what helium is. So sometimes we write it like this now and consider an alpha particle a helium nucleus with 2 protons and 4 things overall in the nucleus. The second type that we found was beta again. So there's the symbol for beta. You write beta, by the way, like this. And what beta really was, it turns out, we later found out, was an electron. Remember, we knew it was negative because it was being bent towards the positive plate and that it was small. So the fact that it's an electron makes sense there. And then the last type that we found there was gamma. And gamma, it's always hard for me to write gamma. It looks kind of like a Y with a really thickly looped part down there. Here's how you spell gamma, by the way. And it turns out the reason that gamma wasn't bent at all, like it had no charge, is that gamma was actually electromagnetic radiation. It was a wave, just like light. And actually, we've talked about gamma radiation before, and I'm going to put it up here in just a second. But we're going to go into more detail in the second video on alpha decay. And then in the third video, we'll go into more detail about beta decay. And gamma, we're not going to get too much more into it except this last bit here, which I'll put up in a second. But actually, before I put that last little bit up, let me talk about how dangerous these are. Because you think of radioactive stuff as dangerous, right? So alpha particles aren't that dangerous, actually. They're big enough that they're fairly easy to stop. So, like, actually, just this paper that I've been writing stuff on. Paper, if you wanted to shield yourself from alpha radiation, you could just use paper and that would stop it. Or even actually, your skin's tough enough. So your skin will stop alpha radiation. But one thing that is dangerous is that you breathe it in. If you breathe it in, the tissues on the inside of you aren't as tough as your skin. And then those alpha particles flying around or something spitting out alpha particles can damage your skin and give you radiation burns. Or worse off, maybe even, is that it can damage your DNA and give you cancer. Beta particles are more dangerous. These little electrons are really zipping along. They're small, so in that sense, they're easy to stop, but they can definitely damage your skin and still hurt you even from the outside. So alpha particles, you'd have to breathe and get something radioactive inside of you, but beta can get you from the outside. It still doesn't take much to stop it. So if you had some aluminum foil and wrapped your head in that, then you could stop beta particles there. It's funny, they still say wrap your head in tin foil, although who has tin foil, right? We use aluminum foil. But anyway, so aluminum foil can stop beta radiation, or some plywood. So it doesn't take a lot to stop that. Let's talk about gamma just a moment longer before we move on to our other videos. So gamma radiation, remember we actually mentioned it before when we did light. So gamma was not a particle like the other two, it was electromagnetic radiation. And if you remember, it has the highest frequency, the shortest wavelengths, and it's the most dangerous, right? Because we had light, and then higher frequency than that was UV radiation, which is dangerous, can give you cancer if you're exposed enough to it. And then we had X-rays, right? Higher than that, so even more dangerous, you shouldn't get too many X-rays, and then higher than that was gamma radiation. So this stuff is pretty dangerous there, and you gotta watch out for it. So now we're gonna move on, watch a video on alpha decay, and then a video on beta decay.